Hello, today we're going to talk about structure 2.2.8 and 2.2.9. This one is all about intermolecular forces. Okay, so let's talk about the weakest type. Generally, the weakest type of intermolecular forces is dispersion forces. And all molecules will exhibit some level of dispersion forces. So everything. Typically, when you're talking about non-polar molecules, these will be the only forces that they exhibit. All right. So what happens when you have a molecule? I'm going to draw my molecule as like a blob, right? You have electrons that are part of this molecule, and typically we're going to focus on the valence electrons. And the valence electrons have some degree of movement depending on the specific molecule. But sometimes all of those valence electrons wind up off to the side. And this is called an instantaneous dipole moment. So like it becomes a little bit polar, so slightly negative, and this side becomes slightly positive as a result. But it is instantaneous, and it just randomly happens. And just as randomly, the electrons would move back, and it wouldn't be polar anymore, right? When that instantaneous dipole happens, it can actually interact with other molecules who might have the electrons all to one side as well. So this side is slightly negative and this side is slightly positive, and you wind up with a weak force of attraction between them. That is the dispersion force. And so these are very frequently breaking and reforming as the electrons are moving randomly. And so they're very weak interactions. Now, the larger the electron cloud, you're going to have stronger dispersion forces. Some people will call these London dispersion forces, but dispersion is fine. So the more electrons you have in the cloud, the stronger the dispersion forces. So you'll typically see like iodine, I2, has stronger London dispersion forces than, say, Br2, because iodine has more total electrons in their cloud. Another thing to consider is that if you have a more oblong molecule, so something that's like a long chain, CH3, CH2, CH2, versus a molecule with a branch. Like this, the more oblong one tends to have stronger dispersion forces because it's more likely to form a partial positive and a partial negative compared to a molecule that is more like globular, because it's more round basically. If it's more round, you're less likely to see those opposite positive and negative sides. So those are kind of your two considerations when you're looking at dispersion forces: the size of the cloud and like how polarizable it is. And indeed, that word might be a good one to remember, polarizable. So the more likely it is to become uneven, the more polarizable. And the larger the electron cloud, or the more like uneven, then the more polarizable. Our next type of force has to do with dipole molecules. So you could have dipole-induced dipole, or just dipole-dipole interactions. And the key thing here is that you're starting with polar molecules. You have to have at least one polar molecule in order to form these. And that is a permanent dipole. Permanent dipole. So that means where you have a molecule that has always has a slightly positive side and a slightly negative side. So here's a good example where this side is always slightly negative and this side is always slightly positive, because of that uneven distribution of electrons around the central atom, the central carbon. From here, you can have interactions with other molecules. So let's say you have an interaction with another of the same molecule. You could have the same molecule here or the slightly negative and slightly positive ends, and it can form interactions there. And that would be a dipole-dipole interaction. Two polar molecules are interacting with each other. Dipole-dipole. These tend to be stronger than London dispersion forces because of that permanent dipole. They don't have the random motion of electrons breaking and reforming, so you're going to have these stronger interactions. You can also, polar molecules can also cause other things to have an induced dipole moment. So if I have my slight negative and my slight positive, this negative here, if I have another molecule, I'm just going to draw it as a blob again, just so you can visualize. That negative is going to repel electrons in this other molecule. Maybe this one doesn't have a permanent dipole. Maybe it's a nonpolar molecule. But when it repels the electrons, it's going to push them to the other side, creating this induced dipole where this side becomes slightly positive and this side becomes slightly negative, and then you can form a weak attraction there. That would be the dipole-induced dipole. Because you have a polar, the dipole, attracting the induced dipole. And these tend to be somewhere in the middle between a dipole-dipole interaction and a dispersion force in terms of strength. But you're still going to see it become like somewhat fleeting because the electrons can still move back and get rid of that temporary dipole that's here. Okay, the third type of intermolecular force you should know about is a hydrogen bond, and this is a little bit of a misnomer. It is still just an intermolecular force. It's a force between molecules. It is not a true bond like a covalent or ionic bond. However, it winds up being stronger than dispersion forces or dipole-dipole interactions because in order for a hydrogen bond to form, you have to have an atom that has a covalent bond to hydrogen, and this has to be very electronegative. Because it's very electronegative, the electrons that are shared in this covalent bond wind up usually next to the other atom. So you wind up with your negative charge almost always on this other atom, and hydrogen becomes partially positive almost always as well. Because of this extreme difference, this is a very polar bond. And this hydrogen can form pretty strong attractions to another atom on another molecule. And usually that atom is also going to have a negative charge to it, partial negative. Maybe it has lone pairs. Maybe it has just one lone pair. Maybe it just has a slightly negative distribution of electrons on that side. But this becomes the hydrogen bond. A good rule of thumb that you can use is FON. Fluorine, oxygen, and nitrogen tend to be electronegative enough so that when it is attached to a hydrogen, that hydrogen can form a hydrogen bond with something else. Oxygen works or nitrogen. So hydrogen bonding is FON, but remember the covalent bond is to the fluorine, oxygen, or nitrogen, and the hydrogen bond is to the other thing, whatever the other thing is. Let's look at water as an example. Water can form these hydrogen bonds. It gives it lots of its unique properties. So this hydrogen can form a hydrogen bond to another water molecule. Remember that these straight lines are covalent bonds, the polar covalent bonds, and we use a dashed line or a dotted line to represent the hydrogen bond. And those tend to be pretty strong. And so in general, the order of strength for these intermolecular forces, London dispersion being the weakest, dipole-dipole interactions are in the middle, and hydrogen bonds are the strongest of the three. Okay, so these different intermolecular forces give rise to the different physical properties of covalent compounds. So the first one I want to talk about are melting points and boiling points. when these molecules are melting or boiling, the only thing that is being broken are the intermolecular forces. I'm going to abbreviate IMF. Intermolecular forces have to break. Some of them break when it's melting, all of them break when it's boiling. So the stronger the intermolecular forces will give rise to higher melting points and higher boiling points. So that is one of the physical properties. Another one would be volatility, for a very similar reason. Volatility has to do with how well it evaporates. So more volatile things evaporate more. So when you have weaker intermolecular forces, you have increased volatility because it will evaporate easier. It will break those intermolecular forces better. Another physical property that it affects is solubility. A really common phrase in chemistry is like dissolves like. And so you'll see things that have very similar intermolecular forces are going to dissolve in similar intermolecular forces. So like polar things dissolve well in polar things, non-polar things dissolve well in non-polar things. And it all has to do with their intermolecular forces. If you have a whole bunch of, if you have a bunch of substances that only form London dispersion forces, then they're likely to dissolve in one another. But if you have something that forms London dispersion forces and something that forms hydrogen bonds, the substance that only forms dispersion forces can't break apart the hydrogen bonding to mix. So that's where you have things like oil and water forming layers, because water forms those hydrogen bonds, whereas the oil is nonpolar and only forms the London dispersion forces. I'm abbreviating there. And the dispersion forces are not strong enough to break apart the water molecules in order to mix. So that's why it does not mix. So always consider, like, draw the two things if you're trying to figure out whether they're soluble. If you draw the two molecules, and if they are likely to form intermolecular forces with one another, then they're likely to dissolve. But if they are not very similar, then they're less likely to be soluble in one another. The last thing that could be affected is something called is electrical conductivity. And typically we're going to be using it kind of as a baseline to determine whether or not it is ionic, because even whether you have polar or nonpolar, when it dissolves, it's still not going to be particularly electrically conductive. Whereas ionic compounds, when they dissolve, they do conduct electricity. And so it's a good way for us to distinguish between covalent substances versus ionic substances. So these are all different things that we can use to test to determine intermolecular forces and therefore the type of bonding present. So for this example, it wants us to place the following molecules in order of increasing boiling point. We need to have an idea about their structure. So the CHO, you're going to see a double bond O, and then the H. This one, it can form dipole-dipole interactions because it has that permanent dipole moment with that double bond O. The CH3, CH2, OH, that OH group can help it form hydrogen bonds with other substances. So that this molecule, ethanol, can form hydrogen bonds. And this last one here is completely symmetrical and is completely nonpolar. So you're only going to see dispersion forces here. So because of that, the CH3CH2 is going to have the lowest boiling point. And then the CH3CHO is going to have the next highest boiling point with the dipole-dipole interactions. Finally, the CH3CH2OH, the ethanol, will have the highest boiling point of the three because of the hydrogen bonds. What experimental evidence could you use to distinguish between a polar and nonpolar substance? You could use melting point, boiling point. Polar substances will tend to have higher melting points and boiling points because they have stronger intermolecular forces, the dipole-dipole interactions. But perhaps easier would be solubility. Polar covalent compounds will tend to dissolve in water well because water is also polar. Nonpolar substances will typically not dissolve well in water. So that is a little bit of a simpler method to distinguish between the two. So this also links to the ideal gas law. And so in the ideal gas law, we assume that the molecules or the particles do not form intermolecular forces. So real gases, of course, can form intermolecular forces. And the stronger the intermolecular forces they form, the more it deviates from ideal behavior. And that's because if you have your container and if your molecules are interacting with one another, it's slowing them down and affecting the collisions that they have with the walls of the container. So it's going to decrease the pressure from what we would expect from ideal. So this kind of links to an interesting topic with the words bonds and forces. So we've been talking about bonding as in ionic bonding, covalent bonding, metallic bonding, even network covalent bonding. And then the forces that we've talked about in this section are those intermolecular forces, where they're between molecules. I think it's an interesting distinction because then we have things like hydrogen bonds, where that word bonds still comes into play. In terms of chemistry, you should know that bonds are stronger and more permanent. Forces can be more easily broken, and they tend to be weaker, especially when you have these molecules that have covalent bonds within the molecule, and then forces of attraction to other molecules. So they are there's a very clear distinction in strength because the forces will be breaking when melting or boiling point, but the covalent bonds will not be breaking. This also links to kind of a TOK concept. How can advances in technology lead to changes in scientific definitions? So like the IUPAC definition of the hydrogen bond. Basically, as we get more and better information, it makes sense for us to update our definitions. That's one of the hallmarks of science, is that as we are learning new things, we have to find a way to either change our ideas or incorporate our ideas into the larger understanding of what's going on. So, even though like older models can still be useful for certain types of understanding, it's always important to make sure that we are staying up to date and all of the new evidence is being incorporated to the best of our ability. We also talked about the types of experimental data. This goes in with like our tools or our inquiry skills. What experimental data demonstrates the physical properties of covalent substances. Make sure you know about melting point and boiling point and how the strength of intermolecular forces affects that. The volatility, how quickly it can evaporate. Solubility, whether it dissolves in polar substances or nonpolar substances and to what extent. And then comparing that to ionic compounds who can conduct electricity when dissolved, whereas covalent compounds cannot conduct electricity when dissolved. This, of course, also links to functional groups when you get into some of your organic chemistry. So if you have things like where you have maybe an alcohol group, alcohol groups have an OH bond. And because oxygen has a high electronegativity, the hydrogen can form intermolecular forces, can form hydrogen bonds with other compounds. So that alcohol functional group determines that it can form those hydrogen bonds. Similarly, if you have an amine group, that high electronegativity of nitrogen means it can form hydrogen bonds. Whereas if you have something like a ketone, ketones are in the center of the molecule, that's C double bond O, and so it makes it have this permanent dipole, and therefore it can form dipole-dipole interactions. And so the type of functional group present in a molecule very much has a major effect on what kind of intermolecular forces it can form.